Hi guys, this is a long review of the paper Transfer Learning from Speaker Verification to Multispeaker Text-to-Speech Synthesis. This paper is a classical TTS paper published in 2018 by Google AI people. And you can see their main contributions is to propose three individual networks and hook up the three networks together. The first is the speaker encoder network, second the synthesis network, Tacotron based, and Tacotron 2 based. And the third network is the WaveNet-based vocoder network. Well, it's all from Google, right? Tacotron 2 and the WaveNet, they're both very good. And I think the main novelty of this paper is the speaker encoder network. And talking about the task, although the authors mentioned and they're trying to say this is a multi-speaker text-to-speech, but in the research community, people more likely to call this thing called a voice conversion instead of their multi-speaker TTS. So the task is in the inference stage, or the generation stage, okay? Speech generation stage. So this is your system. You're going to be given a target speaker's voice, okay? For example, he said, I am Zhang. This is speech, okay? This is one of the input, or several utterances of this, okay? This is speech. And then you're given a text. For instance, I want go home. So this is going to be these two inputs will be sent into the inferencer or your system, TTS system. Yeah, let's call this TTS. And your TTS is supposed to synthesize a target voice, which is I want to go home. But important thing is it sounds like Zhang, or the target speaker. So it has to be sound similar to the target speaker. I think I might get confused. Yeah, I was confused. I want to make a modification here. I think this paper is not voice conversion. This paper is more about the multi-speaker TTS, because it does not have source speech. So this is multi-speaker TTS, I think. So what is voice conversion? Let me write it here. So the voice conversion is you still have the register process, or I am John, the target speaker's voice. You have target speaker's voice. Target speaker voice. Target voice. And you have a source voice. Let's call that source speech utterance, speech recording. It's less confusing. But there's no text. It's a audio recording. Okay. These two are being sent into the voice converter, and the output is same as the TTS. It's speech utterance, right? But it sounds like the target. And you can see that the difference is the voice conversion. You don't have to synthesize or go from text to speech, but the multiple speaker TTS, you do have to go from the text to speech, but in the style of the target speaker. Okay. You may ask, for your multi-speaker TTS, so how does the training look like? Well, here the author gives us their system. I will jump to the abstract later on, but let's first look at their proposed system. For those of you who are not familiar with transformer, search the transformer, or attention is all you need in my channel. Okay. And you can definitely see that the system shown in figure 1 especially go from the synthesizer part. Synthesizer is a transformer. Yeah. What is different is, so this is the transformer. So what's the input to the transformer? Or what's the input to the decoder? And you can see they are using another auxiliary encoder, which is a speaker encoder. So they are going to have a speaker embedding out there. It's going to be concatenated with the encoder's embeddings output. So you may ask, what is the output of the encoder? So remember, I told you that the task is try to go from text to speech. So the input here is a textual sequence. Of course, original text sequence is a word sequence, right? But you need to have something called word to grapheme or word to phone sequence, right? You get grapheme or phone sequence. But these also use the phone sequence. They're doing English, so they use phone sequence. But if you're doing Mandarin, probably you have to use grapheme or character, right? So this is going to be sent into the encoder of the transformer. Okay, the encoder get the embedding, and these two embeddings, one is the textual embedding, right, or NLP token embedding, and the second embedding is a acoustic related embedding. So the text feature and the audio features got concatenated here together. See, and then the attention decoder, and you can see the loop here means it's an auto-regressive structure. It's just standard transformer, okay? And what is the output of the transformer? It's spectrogram. Sorry about my drawing, but it's a spectrogram. So for those of you who do not know spectrogram, Wikipedia it, okay? And then it's gonna be sent into a vocoder. So you may ask, what is vocoder? So anything that ends with the ER means something that's doing something. So the key thing is that it has a code, the VO plus the ER. I think the VO means voice. So the code means it comes from the information theory. It's taking the spectrogram or the spectrum sequence as a sequence, okay? And it takes the output of vocoder, which is the waveform, as another sequence. So when you go from one sequence to another sequence, remember the Second World War, they have this type of enigma, right? Enigma. Yeah, I might say this wrongly, okay? Decipher, okay? Decipher. All it does is try to decompose it or decrypt one input telegraph sequence into something that's understandable word sequence by human being, right? And the enigma in the Second World War is a decoder. So decoder means you always goes from some something that's more difficult to understand to something easier to understand, or AKA, so that the entropy got reduced, right? This is called decoder. And same thing here, but this is inverted. You can see that the spectrogram has a less amount of information than waveform because it's a concise version of waveform. Some people can even read the spectrogram. They can guess what the word is in the spectrogram because the spectrogram gives you concise or it removes the redundant information in the waveform. So when you go from something concise to something with more redundancy, it's the inverse of the decoder. It's called a coding or coder. So this is how, when the Allies they want to send encoded or encrypted message, a telegraph, they want to pass the text through their coder, so they can get some more sophisticated stuff. Same thing here. You get a spectrogram, you pass through to the voice coder, then you got something more sophisticated stuff, waveform. But fortunately, waveform is perceivable by our ears. But the vocoder is just the idea of this. Okay. Okay. Now, I think it's time to take a quick look at their abstract. I think their abstract is very clearly written. I enjoy reading them. First of all, they mentioned that the requirement of synthesizing natural speech. They're saying that say you have a general, you want to train a general TTS, okay? Then think about the general TTS. It's a supervisor training, okay? So the text in, speech out, right? So you got to have a lots of pairs of text and speech, the utterance and its transcription, and it requires high quality, large amounts of data. Google is good at this. Okay. And they're saying this, if you want to support many speakers, and suppose each speaker only has tens of minutes per speaker, it's doable. You can have use all of their data to train this type of a multi-speaker generation TTS. But what if you just have one or two sentences or of this speaker? Then you have to go through a new approach, not the approach mentioned in the citation 8. So the authors, they mentioned that their approach is not to collect as many data from each speaker as possible, because they say it's impractical. And that they are saying that they want to decouple the speaker modeling from the speech synthesis. So let's say this, suppose they regard this, suppose you have a speech. So the speech can be viewed as the combination of two factors. The first is the speaker characteristic. Well, the second factor is the how do you say that? The speaker how do you say that? It's like more like the intelligibility. Anyways, it's getting worse. Intelligibility, speech intelligibility. I think this is a better word. So suppose you have a speech utterance, okay? Suppose you remove the speaker characteristic. What do you get? You get a speech intelligibility. But when you add the speaker characteristic on it, then you heard the personalized speech. So they say, can I just build a model for this? And then build another model of this. And then they combine these two models together, using the two models together to just synthesize, personalized speech. Personalize. So it's clear, right? So this model is more like a TTS. And they're saying that this is the speaker model. Okay, that's their approach. But to be frankly speaking, their thought is not new. This is why they are doing mentioning about other people's work. And these two models are mainly when they combine them together. The TTS model, they're using something called the Tacotron tool. I think by the time you see the video, I probably have already made a video or tutorial on Tacotron 2. You can search the keywords in my channel. And the vocoder wise, they use the WaveNet vocoder. I might want to do another WaveNet vocoder video later on. And they're saying that there are lots of data sets out there. The Deep Voice 3, they support over 2,000 speakers. And this is a good thing because there's a more speaker variation in the training set. So the model should work better in terms of the multiple speaker synthesis. And the 18th reference, voice loop, it could generate the speech from voice and sing during training. What does it mean? So it doesn't mean, it means that normally during my training, I would be able to see John's voice, can see Anna's voice, right? This during training. But in the inference stage, what if I have Mike's voice as the input? This is called unseen case. This is definitely unseen. It's called unseen. And for general machine learning people, this is also called a zero-shot learning, because you didn't train a model from Mike. You only have one example of the Mike voice, and you are asked to synthesize some speech of Mike. Definitely the approach is, the general concept is that this training set, it's not just John and Anna. They have lots of speakers. It might have a speaker, for instance, Phil. His voice together with John's voice, when there are two voices combined together, or somewhat ways of combining together, is somewhat very similar to Mike. So this information can be used as a model to generate the Mike's speaker embedding for the inference. Okay, you get this, right? So this is the concept of zero shot. So although you haven't seen this case in the training set, but there are some speakers which are similar to each other. So you definitely have seen some similar features or characteristics. You can leverage that information in your inference. Okay. And they're talking about their method. It's called a few shot speaker adaptation, which only a few seconds of speech per speaker is available. Well, this is a very challenging task. Remember that suppose you're a talk show host and you only listen to one of your audience for speaking just one sentence, few seconds, and then you're supposed to mimic that person's voice. It's very challenging, although you have lots of experience of mimicking other people's voice. But it's doable for AI, right? They're saying that the first method you can use is called a speaker adaptation method. So you can use just these one or two sentences of that speaker to adapt your existing model. So your model can be fine-tuned to generate the specific speaker's voice. Okay. The other way of doing this is that to use a speaker encoding method, like I just mentioned before. Maybe John's voice and Phil's voice, when their two voices combine together or somewhat mingle together, sounds like Mike. Okay. Or they generate some similar encoding. They're generating a encoding for Mike. So this way, you don't have to do the adaptation, and you can leverage lots of speaker data in your training set by training a speaker encoder, okay, or speaker encoding based neural network. Okay, and this method, according to the author, is significantly more data efficient. What that means, you don't have to collect lots of speech of the target speaker. You can do few shots learning, okay? And it can obtain higher naturalness according to their results. Yeah, of course, it's also computationally efficient because it doesn't need training. Because of the speaker adaptation involves training, lots of training. Yeah, and the author mentioned that there are some people who have already done this, but the other guys, they train the model jointly. They train the model independently or separately, okay? Yeah, I have a question for the author. Because they haven't compared the joint training with the separate training. I just wonder, is there? I just want to ask why you don't jointly training the model. Okay, it seems to me that jointly training is always better than separate training. Right? Yeah, this paper it also needs the linguistic feature. I think I talk about this here, right? Here, linguistic feature. They're using end-to-end based system to do this. That's fairly standard. Let's look at the details of the speaker encoder, okay? Yeah, I think this video I'm gonna talk more about the details. First of all, for those of you who do not know what is D vector, you could probably search in my channel. Maybe I have that video by the time you search it. So D vector is also something proposed by Google guys, but it's named by Google guys, but I don't think it's new, newly invented by the Google. The concept is probably was there a long time ago. The concept is just suppose you have a speaker 1 to n's voice, lots of voice of them. Each speaker may have M1, this speaker have M2's voice, this speaker have MN voice, okay? Utterances. So all they was doing is that they're trying to chop those speaker recordings into segments, lots of segments. So they got a training set of segments, but with the speaker label, okay? So basically they're training a it's very vanilla feed-forward network. I think they mentioned about this is a 3-layer LSTM. The output Y label is speaker label, okay? Yeah, I think it's roughly like this. I think I might be wrong, but I think I read the paper a long time ago. It seems to me that they're gonna use a intermediate layer from the network or something before the final output, and they call got it wrongly. They use the intermediate layers or the layer before the softmax layer output. They call that D vector. Yeah, it's an embedding, okay? It's an embedding. And then they're saying that you know what? I might be wrong. Because I saw L2 normalization, because definitely if you're having the speaker label, you won't have the L2 normalization. I think I might be wrong about this. I think the Y is probably, let me quick look. Maps a sequence of log mail spectrogram frame. I think I'm right. I'm thinking right on this. To a fixed dimensional embedding vector. Okay, they learned this vector. Okay. Oh, this is a learning target. I'm wrong. Oh, I think I'm correct again. Because they're saying that the loss is speaker verification based loss. So I think I'm right. I was right. So you can see it doesn't use the final softmax as embedding, but use some intermediate layer or as a D vector. So this is not new. The reason why I say it's not new, because I think that in the speech domain, long time before the D vector, people have tried a lot something called the bottleneck feature. Lots of people know what I'm talking about. It's something, if you know the variational autoencoder, you know what I'm talking about. But bottleneck feature is more like something like this. So suppose this is the audio feature. Say this is a filter bank feature, okay, of certain speech. And suppose your task is the speaker verification, okay, filter bank features. And you're supposed to get a speaker labels, okay. And then once they finish training this, sometimes it's not speaker label, sometimes it's the CNOs. CNO is the states of the triphones in acoustic model for ASR. CNO is for ASR. It can be either speaker verification task or ASR task. So once you train these things, the researchers, they deliberately made, for example, the DN. Suppose the DN in total they have 7 layers, but they for the third layer or maybe the fourth layer, they made this layer extremely small in terms of number of neurons. So they use this layer's output as a something called a high-level feature or representative feature. But at that time, people don't call that as speech embedding, because this is fairly narrow compared to the output and the input. So they call that bottleneck. It looks like a bottle. Okay, so you can see that the vector is fairly similar to this, but they give it another name. All right, I'm gonna move on. Although the network is not optimized directly to learn representation. Yeah, this is some magic things because you can see that training this speaker encoder doesn't involve the TTS. All it does is just train a speaker embedding or representation. Okay, and it's supervised learning also. But they're demonstrating later on that this embedding, just by vanillally hooking up to the textual feature, it can be used for the multiple speaker TTS. Talking about the baseline is using a fixed embedding. What does that mean? It means, suppose the training set has 100 speaker. So you only have 100 speaker embeddings in the testing. So suppose the speaker is seen, all you have to do is that you pull the embedding of that speaker you train from the training set and using that in your inference. Clear? Yeah. But the other way of their proposed method is that they do not use a fixed embedding. They calculate the embedding using the speech encoder. So regardless whether the speaker is seen or unseen, it will still pass the speaker's target speech into the speaker encoder. Sucks. This is more like encoder, okay. It will get the D vector. You say, wait, what if the D vector is not the same vector as the vector you get from the training set? I would say for the scene speaker, it might be worse because you definitely want to use something that you've seen before. You don't want to regenerate the scene case, right? From your training set. But the biggest benefit is that of using this encoder is for the unseen case. Or think about it when you're using the fixed embedding of each speaker in the training set. So for the baseline, when the unseen speaker comes, you can do nothing, right? Because the training set doesn't have it. But if you're using the speaker encoder based method, you can still pass the unseen speaker's target register speech into the decoder and get a D vector. The D vector might be mix a combination of D vectors from different speakers you have seen in the training set. That's my understanding, okay? So this is the reason why using encoder can handle the unseen case. Yeah, like they mentioned, target audio. And the target spectrogram pass through. This is some details of the parameter. Since they're already talking about synthesizer. Okay, synthesizer. They use a Tacotron synthesizer, right? The input is what? Textual, which is G or phone sequence, right? And the other feature is what? The speaker embedding, right? Speaker embedding. Okay. Pass through to the Tacotron module. And the output is the spectrogram, right? Spectrogram. Anyways. And you can see there, it's interesting, they're not only using the L2 loss, but they use a additional L1 loss. I don't have time to go into the details. But it's interesting because I think L2 loss is good enough. Vocoder. So the third part is the vocoder. So remember I talked about the first part of speaker encoder, synthesizer. This is the first part, encoder, okay? Speaker encoder. First part. This is the second part. The third part of vocoder. I think the vocoder was it just used their proprietary in-house WaveNet vocoder. I think it's very good. It's very, very good. But definitely the vocoder you need to train. Okay, who has lots of good data to train the vocoder. Okay. I think they did some analysis regarding the visual quality or visualized synthesized speech, showing the figure 2. It's not very convincing to me because they are always just saying that, okay, the upper one is the upper one on the left is the male target audio. The bottom two are female. Definitely you can see that this is female. I can tell. Okay, the harmonics, the space between the harmonics is bigger because they have a higher pitch. And they're saying that the synthesizer mass spectrogram, you can see they're talking about the F2. Okay, of course the females F1, F2, F3, especially F3 and F2 are generally higher than the male, right? They're showing this. It doesn't serve as a convincing proof to me that their algorithm improved the speaker similarity, because it's definitely easy to synthesize some speech which sounds like male or sounds like female. It's easy. As long as you made the formant correctly, you're gonna get female and a male voice, but and the pitch correct. Okay, but to me it's hard to tell the speaker similarity from the spectrogram. I think it's better to watch, check the speech naturalness score. Yeah, like they mentioned that suppose you're using the ground truth. What do you mean? What do you mean by ground truth? Okay, ground truth is more like a controlled experiment. In speech, people do lots of controlled experiments. So this is multiple speaker TTS, okay? You're supposed to given a text and target audio to generate something. Audio, sorry, this audio with the text, right? This text. So you can see in the target audio, the guy said, "I'm John," and the audio with text, the guy said, "I wanna food." So the ground truth means that you have the access to the target or target ground truth audio, and instead of using the target audio as input for your speaker encoding or everything, you use this audio in the test set or the supposed to be inferenced audio, and you extract that speaker information and use this as the input of the multispeaker TTS. It's controlled experiment. They also mentioned that it's okay to see what's the best thing you can do in this scenario, right? Suppose you know what you're gonna synthesize. Can you synthesize as good as what you know? The answer is very good. Looping back is very good. Self loop is very good. 4.4 is almost means it's very good. And the embedding table means this is the baseline. Like I mentioned, you have the speaker embedding from the training set, but you can only solve the sync case. You cannot solve the unsync case. Okay, it's slightly worse, but it's not that bad. And the proposed method, you can see for the sync case, it's worse. You can pause the audio, pause the video for 10 seconds and think about why. Pause it. Okay. The answer is, of course, the proposed model would be worse under the sync case because of why? If the speaker is seen, it's better to use the embedding you learn from the training set in the inference, other than passing the target audio through the speaker encoder again. It might generating another biased speech embedding or speaker embedding. But the good thing is that using their proposed model can handle the unsync case, which I would say for the VCTK, the naturalness is very good, very, very good. For Libre speech, I think they also mentioned that because the Libre speech has more noise compared to the VCTK, the MOS got reduced a lot compared to the Libre speech. And they're mentioning an interesting phenomena. Pause the video to see whether you can see that. Okay. The interesting thing is that in the proposal method, it does better on the unsync case than the sync case. This is counterintuitive. Usually in unsync case, you have less known information, you should do worse, right? And they also explained, or they have their own explanation here. I do not fully agree with them because it's not just I subjectively disagree with them, because the lack of a proof to support their subjective judgment. They're saying that this is a consequence of randomly selected reference utterance for each speaker, which sometimes contain an uneven. What is uneven and a neutral prosody? Prosody means the mainly three factors in speech: duration, pitch, and the intensity. Intensity, pitch, duration. These three things adding together is called a prosody. In informal listening, they say this is synthesize the mimic data of the reference. And because in the Libre speech, people tend to have a more varied prosody. And I think they also mentioned that the prosody factor served as a factor in bringing down the numbers. Okay. I didn't quite get it, but let me know if you get it and message me on the comment section. Okay. Experiments. So besides these experiments, they also run I think the most important experiments, which is a speaker similarity. I would say even you get the naturalness of 4.5 or even 4.8, it doesn't mean that you synthesize the speaker's voice, right? It doesn't mean that you have the target speaker's audio. The similarity is important, because I want Obama's speech. I do not want some random person's perfect speech. Even the Obama speech sounds like not that natural to me, but I wanted to see, okay, this is Obama's speech, okay? Although it's twisted or distorted, but it's Obama. I want the similarity to be as close as to 5 as possible, right? So the definition of the MOS of the similarity, I think 3 means moderately similar, and the 4 means very similar. I think 5 means the same, right? And you can see that, look at the result, the similarity column. It can be seen that the result is not very good. You can see the VCTK, they only get a similarity of 1.8. And the libre speech is better. You got a 2.8, right? And they also conclude that the better generalization of the libre speech model in terms of these speaker similarity metric suggests that a training synthesizer on only 100 speakers in the VCTK database is insufficient to enable high quality speaker transfer. And you can notice one thing is that they train on VCTK, test on libre speech, train on libre speech on, and they test on VCTK. I think this is not that. It's okay if you want to do this, but I would like to see that you can split the VCTK into training and testing set, right? Synth speaker and synth speaker, and see how it works. Because definitely VCTK is, I think according to these people, VCTK is a British English, I think. Correct me if I were wrong, right? Okay. And the libre speech is generally Northern American accent, US English versus UK English. How could that be similar, right? That doesn't make sense to me. And of course, if you're saying that there are too few amounts of speakers in the VCTK database, libre speech has hundreds of speakers. You can split that into training and test set, even validation set, right? And see how the similarity is. Oh, they do have this. Sorry about this. I think I read this. Ground truth. I explained the ground truth to you, right? It's a more like controlled experiment. Same speaker, same gender, different gender. You can see that the similarity, if you use the ground truth, it's almost very good for the VCTK, but for libre speech, it starts to degrade because it has noise. If you're using the embedding table, which is the baseline, right? You're using the embeddings you learned from the training set under the sync case, you can see the VCTK is still very good, I would say. It's still very good. And the proposal method, I think this is interesting to me. For the VCTK, which is a clean corpus, the proposal method similarity wise is better than the embedding table. So you can see that even, I think this is the benefit of using this speaker encoder, which was trained on 1.8 thousand speaker they have. You see, they trained on a very large set. Oh, it's not 1.8 speakers. It's 18,000 speakers. That's a huge amount of, I would call that an external database, right? Because when you're training your model with your baseline, you don't have this external speaker database. So the data you have seen is limited. although the same case, you can just directly use the embedding you learn from the training set on here. But I think the proposed model, it's benefiting from this extra external speaker database, and this is slightly better. But for Libby speech, it's getting worse. I think, generally speaking, I think I would contend if under the same case, the proposed model is worse than the baseline. And especially for the unseen case, just something called one-shot learning. Yeah, I would call it one-shot learning, or few shots learning. The VCDK degraded significantly, or very much. The similarity is 3.3. I think it's still not that worse. It's still above 3, right? Not that bad. And the Libby speech is still above 3. That's fine. And you can see that the degradation happened to Libby speech is only 0.2%. So, which is a good thing. So imagine that you could have a lot of clean recordings, so it might be getting better things. Okay, but I assume that you probably achieve 3.5, at least 3.5. That's my gut feeling. Okay, in terms of the similarity MOS. And they mentioned that the proposed model achieved about 4.0 MOS in all dataset, with the VCTK model obtained at most about 0.2 points higher than the Libby speech model when evaluating on scene speaker. I think this is a consequence of two drawbacks of the Libby speech. The first is the lack of the punctuation in transcript. Yeah, Libby speech doesn't have punctuations. But what if you just apply some NLP model or learn from the audio and add some punctuation? And the second reason is that, yeah, it's noisy. Okay, I think I roughly finished. They talk about the speaker verification ER. I don't think that can be serving as a indicator to tune your multiple speaker TTS, because even having this ER raised, because the speaker verification ER does not equal to the speaker similarity. So even you have an ER of 0%, it doesn't mean that you have a similarity of score of 5. Okay. Speaker embedding space. Oh, here they do some drawings. I think this is common sense, right? This is common sense. Seems that they have because anything you project to two dimension, okay. Anyway, even so, philosophically speaking, even you have this figure, it doesn't mean that this model or this feature space is not very good, because feature space is always a high dimensional space. It's like a manifold. Even if you cannot find a classification hyperplane in the 2D domain, it's likely that you can have a very good classification hyperplane in the hyperdimensional space, right? And they also compared the performance using speaker encoder and training different data sets. Yeah, of course, this one is the best. You see, this tells you that, okay, you gotta work on the data, set up your studio and start to record as many speakers as possible. Because I think up to the first 1, 2, 3, 4 rows are the public available data you can obtain. And you can see that starting from, yeah, the similarity number is getting up. Yeah, but it's significantly lower than 3. I think I would contend with 3 in terms of a similarity, but 2.5 is not good enough. Yeah. They also compare the number of speaker encoder training speakers. I think this is trivial. I will skip this. Fictitious speaker trivial. Skip this. Conclusion. I'm not the author. I wouldn't do the conclusion, but I can quickly go over it. They propose this type of 3-stage TTS synthesis. You have this 3 separated modules. They train separately. They also, I think one thing they're talking about is, I forgot to mention it previously, I think it's for the vocoder. They're saying that since they're using the Libre speech, the database is noisy, it's better to retrain the vocoder using the predicted spectrogram rather than the original spectrogram. Makes sense to me. And they're saying that transfer learning is very critical to achieve these results. I agree. That they also demonstrate that the model is able to generate realistic speech for fictitious speaker. Yeah, fictitious, they also mean they means unseen speaker. Okay. And the authors are very frank. They're saying that they're not attaining the human level naturalness yet. Although they are saying that their WaveNet vocoder is very good. But I guess if you have a lots of single speaker's voice, it's the same speaker, you can do better. I think that's an easier case. Yeah, just like they mentioned. I think if you have a sufficient amount of training data, I think the problem would be a bit alleviated. But I think the authors would continue to explore the case that when there's not enough amount of training data, what are they supposed to do? All right, I'm gonna stop here and see you next week.